Good morning, everyone. Welcome to the fourth day of Capra. We'll get started in about 5 or so minutes. So hang in there. All right. Good morning, everyone. Welcome to the fourth day of Capra. Today's theme is mostly more numerical simulations and applications of numerical relativity to problems in Emery physics. Leo Stein has generously, on zero notice, agreed to be our chair for this morning's session. Right now I'm screen sharing my the schedule for the day. You can see, as I mentioned in an email either earlier this morning for you or last night for me, that we've shifted the schedule a little bit relative to what we've been doing. So the first block of talks will be a little bit longer. We'll take our 1 hour break after the first block of talks, so from 9 to 10 Central Time. We'll come right back at 10. That may trample a little bit on the end part of the LIGO webinar. I'm not sure how long that's going to go for those of you who are going to watch that, but we will try to start more or less promptly at 10 because we'll have a rather shorter break at 11, just 20 minutes before moving into the discussion, which Peter Diener has generously agreed to lead that discussion. So we're now a minute past the hour, so I think it's about time we get started. I'm going to turn things over to Leo and our first speaker of the day.
Okay, thanks, Aaron. Can everybody hear me?
Yeah.
Okay. Well, I guess it's not important to hear me, but more important that Harris starts sharing his screen. So I'll try to keep things on time so that we don't run over the beginning of the LIGO webinar. So I'll give people warnings at the 5 minutes before your talk time and 2 minutes before your talk time is up. So I again recommend 16 plus 4 as Aaron's been running everything before. All right, so I'll stop cutting into Harris's time, and Harris, please take it away.
Hello, thank you, Leo and Aaron. Okay, so I'll be talking about a discontinuous collocation method for self-force application. This is work done with Leo Barak and students Michael Boyle, Pablo Brubeck, and Lydia Gomez da Silva at Queen Mary. So we've heard this week about methods for solving the Tucholsky equation or Reggie-Wheeler equation, the MST method, that apply in the frequency domain. We know that for highly eccentric orbits or unbound orbits, we need to sum over thousands of frequencies, and that these methods are very slow because you have to sum over terms that are very disparate in magnitude, and that required software arithmetic in Mathematica. So one would really want to have a method in the frequency domain to be able to compare results and also be able to do a self-consistent evolution. And there are many groups that have been improving methods that we use for solving the Tucholsky equation in the frequency domain. So the methods, common method used is the method of lines, which involves usually reducing the system to a first order system in time, and then evolving as a system of ODEs that are coupled through a matrix operator that is a differentiation matrix. Now, this method can be used when the fields are smooth, which is true when the source is smooth. But if the source is a delta function, as it is in the Reggie-Wheeler equation for a particle source in an emery, or the Tucholsky equation, in this case, a discontinuity in the source, the source being distributional, makes the solution discontinuous. So if there's a delta function source, then the derivative of the field psi is discontinuous. And if there's a delta prime source, then psi itself is discontinuous. So the methods that have been used so far to overcome this have involved various treatments of the delta function. For example, a group in Jena treated the delta function as a Gaussian pulse, and the other groups used a finite difference representation of the delta function. So the Gaussian pulse method is easy to implement, but it's not very accurate, especially if you want to use pseudospectral methods. The finite difference representation is second order, and it's not very clear how to generalize that to higher order, or to generalize it in to use with a pseudospectral method. The most accurate treatment so far has been to use a time-dependent grid that splits the domain left and right of the particle. This is the most accurate way to do it. You can still use a pseudospectral method and get exponential convergence. However, it's also the most difficult way to handle this. It requires a lot of coding. So you can think of this picture as a Lagrangian picture, where your coordinates follow the particle, and then you split the domain appropriately. And then Peter will talk more about that later. Peter Diener. Then you have to, if you want to add hyperboloidal layers, you can do that near the horizon or infinity, but that means you have 4 subdomains. So what I wanted to do was treat this in as an Eulerian picture, where I can keep my fixed grid and pick whatever slicing I want to, whatever coordinates I want to, and fix those coordinates so I can store my differentiation operators in memory. Yeah.
Sorry to interrupt. You may have the stream running in your background because we can hear your voice twice.
Okay. Hold on a second. Let me lower the volume. Is this better?
We can still hear it. Oh, I'm sorry. It's probably on my end. Is no one else hearing that? I apologize. Please continue.
Okay. Okay, so I would like to have an Eulerian picture where the particle moves freely in our grid, and we can keep using our own choice of coordinates. So to do that, one could take advantage of the fact that the jumps in the solution, psi and all of its derivatives across the particle, are known in advance from the field equation. So the first order derivative, second order derivative, and so on, you can always calculate those without actually solving the PDE. And you can use them as input for your numerical method. So this is what I'm going to describe here. If you consider the usual Lagrange interpolation method, you start from a set of coefficients that are unknown. And then with the method of antideterminate coefficients, you can determine them by imposing a number of collocation conditions, and solve a linear system of equations. And then you get a polynomial, a Lagrange interpolating polynomial, which I write here in a Lagrange basis. The analogous procedure when there's a discontinuity is to use a piecewise polynomial, which has a jump. It's not a polynomial because it has a jump in its coefficients across the particle. So it's basically 2 polynomials, one left and one right of the particle. But then you impose those collocation conditions in this piecewise polynomial. However, now this doesn't close the system because you have more coefficients than conditions. So you need a number of extra conditions, and these are the jump conditions across the particle. And once you close the system, you can solve this this linear system. And the solution is written here as a generalization of the Lagrange interpolation formula. So you can see you still have the Lagrange basis polynomials Pj of x, and there's a correction delta source of delta of x j minus xc and x minus xc. This allows us to do various numerical operations such as differentiation, integration, and so on by simply differentiating the generalized Lagrange formula that we see here. So if I want to compute the nth derivative of this polynomial at xi, then all I need to do is use this differentiation matrix that comes out of differentiating these polynomials. This is what we did before for the usual Lagrange interpolation. But now we have this extra correction term delta that shows up in this formula. So this is nice. Okay. I have 5. So this is nice because it means I can keep using the methods that apply to smooth methods, but with a particle, as long as I model the particle using this function. So here are some results using cell force on a scalar particle in Schwarzschild. This is using equidistant nodes. This is using pseudospectral nodes. As you can see, the second one is much more accurate. So this is just interpolation. This is showing the convergence or the error for doing that interpolation. And now I want to show a quick simulation. Hopefully you can still see my screen. So this is, if we consider an example from a paper by Scott Field, where you have a Reggie-Wheeler equation, but set the potential to 0 and compare the numerical solution to an analytical one, then this is what we get. So you can see a discontinuity here. So although this solution looks fine, if you dig a bit deeper and look at the error is very large. It's about 0.1 or 0.01. So we have been thinking about this for a while and trying to see why this was happening. And the reason this is happening is because what I just described tells you how to do the differentiation in space, but it doesn't treat the discontinuity time in the method of lines. So what we need to do is model the discontinuity in time as well. A normal Runge-Kutta method would not be suitable because it's made for smooth functions, not for discontinuous problems. So you need to come up with a generalization of those methods that treat discontinuities. So we did come up with one. So it's a generalization of the trapezoidal rule or the Hermite rule that includes jump discontinuities. And once we model that correctly, then our accuracy improves a lot. So this is the result with the second order method. And if you look at higher order methods, so we looked at the fourth order method, then we get fourth order convergence. So our error is about 10⁻11 here. 1 minute. And let me also look at, because our method is time symmetric, it conserves energy. So I'm having an issue here. Okay. So this is a Runge-Kutta method, for example. As you can see, it violates conservation of energy because it's not time symmetric. And this is another example where we use a time symmetric method. And you see that energy is conserved to almost to machine precision. Okay, so generally I recommend not using Runge-Kutta type methods or explicit methods for cell force, because they come with a Courant limit and the energy is not conserved. For cell force problems, it's much better to use implicit methods because they are unconditionally stable, energy is conserved. You can find more information on this paper below. And importantly, they don't come at extra cost, because for linear systems, for linear PDEs, you can just invert the matrices and store them. So the performance is the same as with a explicit method. So to conclude, this method has high accuracy, especially if you use pseudospectral nodes, but you could also use it with finite differences. It's an Eulerian picture. That means the grid can be stored and your particle can move freely within that grid. The discontinuity doesn't have to be on your grid points. So you can avoid coordinate mapping and domain decomposition. and you can use a single hyperpoloidal slice for the whole spacetime if you want to. It's quite easy to implement. There are some disadvantages. So one is that you have to use a rather large number of jumps and use it as input for the method, which you need to calculate analytically, and you need to update this function delta as the particle moves. There is a paper by Lear Barak and Paco Judis on how to solve the equation for the Hertz potential and use that, the Tucholsky equation for the Hertz potential, and use it to reconstruct the gravitational cell force. And this is our plan. This is what we'd like to do next to this method. And this is a promising way to do a self-consistent evolution under the influence of the cell force. And thank you.
Thank you, Harris. Sorry that I had to rush you along a bit. I'm looking to see if there are any hands. I don't see any hands. Well, could I ask you to go back to your convergence slide? Because it went by very quickly.
Okay. Here it is. So this is the convergence depending on how many jumps you keep in this expansion. So if you keep no jumps, then you have the usual Lagrange interpolation formula, and that's the top line. Here it converges very, very slowly. Whereas if you keep a number of jumps that's around half the number of grid points that you're using, then the convergence is optimal. And you see that the order of the method is basically the same as the number of jumps. So the slope of these lines is m, basically, where m is the number of jumps you keep. So you do not get, although you're using pseudospectral grid points, you do not get exponential convergence, but you can get high order convergence by keeping a large number of jumps.
So, I mean, I feel like if your number of jumps that you kept also ran with n, like if it was fixed to be n over 2, would that lead to exponential convergence?
Well, this is what I'm doing here, but as you can see, the slope is, it's a log linear plot, so it's not exponential.
Okay, but so I guess this is at m fixed, but n varying.
Oh, I see what you're saying. So yes, so this is m fixed, right? So I haven't tried what you said, so I could try that.
Okay.
I mean, the rule of thumb is that yes, that m should be roughly half the number of the grid points.
Okay. I still did not see any other hands go up. Is that true? All right. Well,
can I ask a question?
Yeah.
Peter, go for it.
Okay. So in the convergence plots, there are how many? Is that the total number of collocation points over the whole grid, or do you have?
Yes. This is the number of points in space.
Okay. So
the other plot I showed in Mathematica was convergence with respect to time.
Okay. Cool. Thank you.
Yeah.
Okay, so maybe we should thank Harris again and
thank you.
Ask Jonathan to share his screen.
Mute. What's happened to my mic?
Okay, we can hear you now, Jonathan.
No, don't do this. I hate Windows. All right.
We can hear you.
Where has my Zoom control panel gone? There it is. It has decided that it wants to mute me for some. There. Can anyone hear me?
We can hear you, and we can see your screen.
Can anyone hear me?
Can you hear us, Jonathan? We can
We
hear
seem to
you.
have lost audio. Okay, I don't hear anything. I can't hear anyone else, but my speakers claim to be on. I will just ignore that and hope that this is working. So, where the devil did all the... There. Okay, now can someone say something?
Can you hear us now?
Yes, thank you. I'm sorry.
All right.
The computer has various issues. Okay.
Yeah, please go ahead.
I'm sorry for the tech issues. There we go. Hopefully, if this thing will now go to full screen. Oh, close enough. Okay. So now that's lost it again. There, full screen mode. All right, thank you. So I want to talk about the Lorenz-gauge dipole mode instability and what to do about it in the time domain. And let me begin by thanking my research collaborators. A large part of this work was done in collaboration with Sam Dolan. And as you'll see in the more recent parts, I've made considerable use of an effective source kindly computed by Barry Wardell. If we think about metric perturbations in general relativity, usual setup, we look at the, we consider a background metric that's a solution of the Einstein equations. We consider metric perturbations. We define the trace reverse metric perturbation, H bar. In a completely generic gauge, the first order perturbed Einstein equations have this set of terms where the Riemann tensor and all the covariant derivatives and the box operator are all defined with respect to the background metric. In practice, that's a pain in the neck. So we usually impose the Lorenz-gauge condition, which kills off those red terms, leaving us our usual relatively nice wave equation for the evolution. This has a lot of nice properties, which I want to briefly review. The key one is that in the Lorenz-gauge, point particle perturbations are nicely behaved. They look like a nice 1/r Coulomb fall off away from the particle. They're spherically symmetric at the particle. Our gauge is non-singular and smooth everywhere. There's no strings. We know how to do regularization in Lorenz-gauge. And as we heard on Tuesday, a Lorenz-gauge metric is, roughly speaking, what you'd like as input for the second order source term. So it's useful if we can compute in the Lorenz-gauge. In this talk, I want to focus on trying to do time domain evolutions in the Lorenz-gauge. This is a program that was laid out very nicely by Barak and Lousto in their 2005 paper. This gives you a direct access to the metric perturbation. By now, there's lots of numerical methods for this type of coupled wave equation, and Barak and Lousto demonstrated this works nicely in Schwarzschild. Barry and I were able to show that this also works well in curve for a scalar field toy model. And modulo the low order mode issues that I'm going to spend most of my talk talking about, there's a clear route to doing generic orbits in Kerr. There's also a clear route to orbital evolution, to evolving, to changing the orbit concurrently with the self-force calculation. Of course, there's always problems. We now have a system of 10 coupled PDEs for the 10 independent components of the metric. We have to monitor and enforce the Lorenz-gauge condition. And most importantly, in the focus of this talk, there are stability problems for the L equals 0 and 1 modes. So what are those issues? The stability problems we think are generic and don't depend on the background. So it's convenient to look at them in Schwarzschild, where we can decompose things into YLM modes. Once we do that, we find that the L greater than or equal to 2 evolutions are stable, assuming one uses an appropriate constraint damping scheme. And again, Lior and Carlos showed this back in 2005 using a constraint damping scheme from Karsten-Gundlach. The L equals 0 monopole and L equals 1 dipole modes are unstable in a naive evolution. Lior and Sam found a generalized Lorenz gauge, aka gauge driver, which will stabilize the monopole mode. But they were unable to stabilize the dipole mode, and that dipole mode is the focus of what I want to talk about. What do we know about this dipole mode? We know that it's a pure gauge homogeneous solution of the first order perturbed Einstein equations. It satisfies all the reasonable physical boundary conditions. It's present generically, whether there's a source term or not, and it appears to be unique for a given background metric. In fact, Lior and Sam found an analytical solution for this gauge mode for Schwarzschild. And its other key property, after initial transients go over, this gauge mode grows linearly with time. This doesn't grow exponentially, it only grows linearly. That's still not good, but it's much easier to handle than an exponentially growing mode. Here's an example from some joint work I did with Sam Dolan. He and I wrote a code to explore this, and that gave us the sort of the genesis of what I'm going to talk about today. You can see this is a norm of the metric perturbation, its time derivatives as a function of time. And you can see that after a while, it just starts growing linearly. And this is true in both the sourced and a vacuum evolution. I have a movie of this, but in the interest of time, I'll skip over that. What can we do about this linearly growing mode? Historically, one way to deal with it is to work in the frequency domain. That implicitly lets you say there's no linearly growing mode, effectively enforces boundedness as t goes to infinity. And I'll mention the caveat. That's if all your frequencies are lower bounded away from 0, because obviously an infinitesimally small frequency looks just like a linear drift. A linear drift looks like the very first part of a very long, very tall growing sine wave. But if you can work in the frequency domain, that kills the growing mode very nicely, and a number of people have used this. Another possibility is if we stay in the time domain, for circular orbits, the growing mode has the frequency of the particle motion, times m, and Lior and Sam found that a frequency domain notch filter could remove it. Still another possibility is just to live with it. It's purely a gauge effect. We're still in the Lorenz gauge. It's just the Lorenz gauge is sort of drifting off sideways in the XY plane relative to where our big black hole is. This has various issues, but it's at least a possibility. Sam Dolan and I experimented with changing the gauge driver conditions, and I ran numerical tests on about 1 million possible sets of gauge parameters. We were unable to find any gauge condition, any set of gauge parameters, which eliminated the growing mode. At Capra in 2016 in Moudon, I proposed orthogonalizing the right-hand side of the evolution equations with respect to the linearly growing mode. This was enough to stabilize vacuum evolutions, but it failed when I turned on a source term. So instead, at Capra 2018 at the AEI, I propose orthogonalizing the metric perturbation itself with respect to the linearly growing mode. The idea here is choose some inner product on metric perturbations and their time derivatives, the state vectors. This implicitly also defines a norm, and I usually just use the standard Euclidean inner product. Got it, Leo, thanks. Consider a sourced evolution with some initial data. In parallel with this, also run a vacuum homogeneous evolution with the same initial data. Then form this linear combination where you choose this scalar lambda, just a complex number, such that the new so-called orthogonal solution is in fact orthogonal to the homogeneous mode. And lambda is a constant, you update it occasionally. If you do this, U ortho is in fact a solution of the sourced evolution equations, but hopefully it doesn't have the growing mode. Here's a numerical example from this project Sam Dolan and I did. Notice that was the original evolution. Now, if I turn on the orthogonalization, now the norm just sits there and you can hardly see it. If I zoom the vertical scale, you can see the norms oscillate a bit, but do not grow in any unbounded fashion. And in fact, this lambda is approximately just minus one in its real part and 0 in the imaginary part. I also have a movie of this, but again, I'll skip over that so I can show you a new movie. So there's lots of variants of this. For instance, instead of orthogonalizing say every 10m or something, you could orthogonalize on an orbit averaged basis. You could also orthogonalize over the entire history of the evolution. The sort of mental model you should think of is AC coupling in electrical engineering, where if you think of an oscilloscope where the input signals always have a switch for AC coupling versus DC coupling. We want AC coupling to kill off this quote unquote DC growing mode. The examples I showed you use a delta function effective source. It's less clear how to handle an effective source. I have some ideas on that, and I'm working on that now. I have a new code under construction to experiment with these and other ideas. And this uses Barry Wardell's effective source, and to help in debugging, to help distinguish violations of the Lorenz-gauge from violations of the Einstein equations, there's a separate computation of the Einstein tensor done separately with separate code generated out of Sage manifolds. So I want to show you a movie of that. This code's currently coming on the air and testing. And so let's see. This shows the metric perturbations in red, green, and blue, together with this thin black line is the Lorenz-gauge constraint violation. The heavy black line is the Einstein tensor norm. And you can see that the Einstein tensor norm violations radiate away. Our initial data is gauge constraint violating, so the Einstein equations aren't satisfied either. But everything settles down after a couple of hundred M, after about 100 M, to a nice smooth system where the field perturbations oscillate. This is an odd parity, so there's just the 3, 8, H bar 8, 9, and 10 in the usual tensor decomposition. And everything looks nice far from the effective source. Near the particle, near the world tube, there's some tricky things going on, and I'm not yet sure what's generating, but I think the way I'm doing the world tube is generating gauge and Einstein equation violations. So I'm still working on that. This code is quite new and is still under development. So to summarize then, doing time domain evolutions in the Lorenz-gauge has a lot of nice properties, but there are these unstable modes, this dipole mode. It grows linearly with time, and it's unique for a given background metric. So it seems to be possible to orthogonalize the metric perturbation with respect to the homogeneous mode. And this has passed initial tests, and I'm now working on a new code which is allowing more thorough tests, verify that I can get correct self-forces in Schwarzschild. I want to try eccentric orbits. I want to try both point particle and effective source regulations. And if this works, of course, the next step will be to try Kerr. Thank you for your attention.
Thank you, Jonathan. Does Aaron, oh, that's the clap icon, not the hand icon, sorry. Harold has a question. Harold, please go ahead.
Yeah, it's nice work, good to see this. How obviously easy is it to find the homogeneous solution in generic spacetimes?
Basically, because this is an unstable mode, all you do is you start off an evolution with your usual evolution, but no source terms and some non-zero initial data, and then evolve for a while. And after a while, the growing gauge mode will take over and will dominate the solution. And if you want to get a little bit fancier, what I've done is I've taken, because there's some tiny trace of effects of the initial data, evolve for, say 500 M, and then say, what's the difference between the solution at 500 M and the difference at 1000 M? There's issues there with, you want to be multiples of an orbital period. And for inclined generic orbits in Kerr that are non-resonant, figuring out the right, quote, orbital period, unquote, is a bit tricky. There's still some issues there on that. But I think fundamentally, finding an unstable mode is usually pretty easy. We have to work to get rid of it, but getting a solution with the unstable mode is usually happens without any effort.
Any other questions? So, Jonathan, maybe you could explain this to me, that I might have missed it. When you talk about taking these two solutions, the inhomogeneous one and the homogeneous one, and
Yes.
forming this linear combination, are you basically saying you just live with the linearly growing mode in both cases and post-process the results? Or do you co-evolve these two systems and then take the data and like reset the solution for the inhomogeneous system?
Well, actually, the latter thing is what I did in my very first implementation. I did separate homogeneous and sourced evolutions, and then wrote a post-processor which read the data files of the metric perturbation in each one, and formed the right linear, computed the lambda and formed the right linear combination. But the cleaner technique is to, in fact, run the two evolutions in parallel, and at every time step form the appropriate linear, at every time step, or however often you feel like looking at output, but each evolution is running independently, form the right linear combination and look at that. But yes, each evolution still has the growing mode. But the idea is, because it only grows linearly in time, you can actually tolerate its presence. It's just you don't really want it in your output because it's a pain in the neck, and it makes it hard to recognize periodicity and so on. Does that sort of answer your question?
Yeah, maybe, but maybe I still don't understand something. Do you, to figure out the correct linear combination to take, is this inner product that you use an integral not only over space but also over some period of time of the solutions? I talked about that as an option, but I have not done that. What I've always done so far is to simply say at the moment when I'm going to compute lambda, I take that inner product, which is literally just a sum over grid points of the usual Euclidean dot product in practice, and compute the lambda from it by straightforward linear algebra. I see. Okay.
There somewhere. There, yeah. Basically, this is you just you solve the condition that this sum is orthogonal to u dot home, and that gives you a linear, and that gives you a linear equation for lambda, a scalar equation, just as complex numbers, involving the dot product of the homogeneous solution with itself and the dot product of the homogeneous solution and the source solution. So the calculation is very easy.
I see. Okay, thanks. Okay, I think it's time to move on to Peter's talk. So let's thank Jonathan again. And Peter, if you could please start sharing your screen.
That should work. And
yep,
we can full screen.
We can see your screen and we can hear you.
Excellent.
So please go ahead.
Okay, so as usual at this time of year, I will give my update on our quest for self-consistent evolution of a scalar charge around a Schwarzschild black hole. We know that there's a lot of techniques where you can calculate very accurate frequency domain cell force information for the cell force, and then one way of evolving that is to use these geodesic-based cell forces and then drive a motion of the particle where you neglect the fact that the particle was not moving on those, was not on that geodesic in the past. So this is what Niels and many other people have been doing. So here you actually do the evolution in a post-processing way. So the evolution and the waveform generation can be very fast, and you also use very accurate cell forces. But you do rely on this slow orbit evolution where you neglect the part of the cell force that comes from the fact that the orbit was changing in the past. Alternative, and what I've been working towards with Niels and Barry for some time, is to compute the true cell force while simultaneously drive the motion. So this has to be done in the time domain. So of course, it's potentially slow and expensive, and potentially we have less accurate cell forces. So the main reason why we want to do this is not so much to be expected to perform the full evolution, because that would probably be very expensive in computational cost, but hopefully be able to do long enough evolutions to check errors in the geodesic evolutions, and potentially also investigate things like resonances once we have all this up and running in Kerr. So for up to now, we have used what is called the effective source approach, where the idea is you compute a regular field, psi r, such that you can just calculate the cell force as the gradient of that psi r. And the psi r, of course, is the full retarded field minus some singular fields. And of course, this is the Detweiler-Whiting singular field. And the idea is they can approximate that via local expansions. So you get an approximate Detweiler-Whiting singular field that depends on the source position, the field position, the source position, for velocity, and the current acceleration of the particle. You can then, using this approximate Detweiler-Whiting singular field, you can plug that into the field equation and generate an effective source for the regular field. And the main problem that is important for this discussion here is that the approximate Detweiler-Whiting singular field depends, as I said, on the source position for velocity and acceleration. But when you plug it into the field equation, you have to take two time derivatives of the Detweiler-Whiting singular field. And that means that the effective source will actually depend on not only the field position for velocity and acceleration, but also the first and second time derivative of the acceleration. And this is one of the main problems that we have to address. So the status at last year's Capra was that we have a 1+1 D discontinuous lurking code with time-dependent coordinates as well as hyperlocal slices that had been rewritten and released as open source software and included in the Einstein toolkit. At that time, we were still plagued by instabilities under most circumstances when the back reaction was turned on. The only time when we seemed to be able to do stable simulations with the back reaction was when we left A dot and A double dot out of the effective source. And so one observation is that A dot and A double dot is actually only needed when they evaluate the effective source away from the particle. They don't contribute when you evaluate things at the particle itself. So in a numerical scheme, the main problem is that we have to use finite differencing to calculate A dot and A double dot. And this adds a lot of numerical noise to the simulation. And we suspect that is what is causing the instabilities. So at last Capra, Barry suggested to try to shrink the world tube down to 0 size, and then only use the effective source to calculate the jumps in the field and derivatives at the particle itself. Actually, there's only jumps in the radial derivative in this particular case. So this is essentially switching from an effective source scheme, where you have an extended source, to a real delta function point particle description, where we would then evolve the retarded field everywhere. And it seemed that it would actually only require minimal changes to the code. So I decided to go ahead and try that. And so essentially the idea is that before, if you look at the purple curve here, is what we normally have when we use a world tube. We have the world tube goes from here to here, and we have a finite and regular field inside that location, and then we have the full retarded field outside. And so we have to, when we calculate discontinuous Galerkin fluxes across this boundary, we of course we have to add and subtract the jumps in the derivatives across those boundaries. You may have noticed that there's a little bit of discontinuity here as well, but this is because we are using these time-dependent coordinates from Field and et al. Inside this region, and outside we're using hyperboloidal coordinates. So we use different coordinates in different regimes, but we can again take care of those discontinuities if we just keep the discontinuous element boundaries at those locations and just correct for the different coordinates when we calculate the fluxes. So the new idea was to essentially shrink this world tube down to 0 size and go for the full retarded field everywhere. And then, of course, we have jumps across, and here I'm showing the radial derivative of the field as a function of the radial coordinate. And so we will have to, the idea was to use the effective source to calculate these jumps and still have things work as before. And so after making those fairly simple changes, I did some tests and found that, well, initially it looked like everything was working fine. I plot the world tube simulation in purple, and the green seems to be right on top of it. Unfortunately, this is only true when you actually when you just use the eyeball norm here. So if I actually look more detailed here for a slightly different case, we found that for different discontinuous Galerkin orders here, when we use the world tube, the errors was of the order 10 to minus 14, and here the accuracy is determined by the accuracy of the initial data we used to start the simulation. Whereas with the delta function approach, the errors was about 5 orders of magnitude higher. And also, it was converging rather slowly. Or it is converging rather slowly. If I just focus on the top 3 curves, I can see that if at order 6, if I compare order 6 and order 8, if I multiply the order 6 or order 8 errors by a factor of 1.69, the curves lie right on top of each other. And for the order 10, if I multiply by an additional factor of 1.52 error, the error again lies right on top of each other. And you might wonder, where does these numbers come from? And it turns out that when you increase the order of the scheme, the collocation points gets distributed slightly differently. In discontinuous collocation schemes, the collocation points tends to be closer to the boundaries. And so when I go from order 6 to order 8, the minimal distance between nodes in the collocation points is essentially is exactly a factor of 1.69. And when I go from order 8 to 10, there's an additional change in the node location of a factor of 1.52. So it looks like currently that the error is completely dominated by the minimum node location, but on the grid. And this, of course, is not good. And so apparently, when I did this change, I do something really stupid when shrinking the world tube size to 0 that makes the convergence only linear in the smallest node separation. I have spent some time looking at the code, and I have not yet figured out what I'm doing to cause this, but I'm hopeful that I will be able to figure that out. So hopefully, long before next Capra, I will fix this and test whether shrinking the world tube helps on the stability of self-consistent evolution. For other information about the code, so as I mentioned at last Capra, the code had been included in the Einstein toolkit, but now the code is also part of the black hole perturbation toolkit as well. Last summer, I had an IU student who worked on a Tarkovsky code in Schwarzschild and the beginning of figuring out how to do that in Kerr. And this summer, I have another IU student, Joe Gibbs, who is in the process of making that part of the code. Also, I have another IU student, Mary Ogborn, who this summer is adding a checkpoint B-start capability to the code. And Sam Cupp, who will be talking next, is currently working on the Lorenz-gauge of the Redi-Wheeler-Cerulli metric perturbation codes. And so, as usual, I have not yet reached the goal of doing my self-consistent evolutions, but I am really hopeful that I will be able to fix this problem and hopefully bear a suggestion of so that we don't actually need a dot and a double dot anymore would be what will allow us to
Did we lose Peter?
I think so.
Okay. Well, that's rather unfortunate since he was just on his Outlook slide. Let's wait a second and see if his network is still connected.
It says he's still connected, so maybe his mic, we've just lost his mic. Maybe not.
Okay, so it looks like Peter has dropped off of the connection. So my suggestion is that if anybody has questions for Peter, we should save them for when he reconnects, which is hopefully soon. So maybe we should put Peter's question time after the next talk as well. So doesn't look like Peter's reconnecting. So is Samuel connected?
Yes, I'm here.
Okay. Do you want to start sharing your screen?
Yeah.
And let's hope that Peter reconnects, but if not, then And I guess we'll just move on to your talk.
Does this look good?
Yes, we can see your screen and we
Cool.
can hear
Oh,
you.
there's
There's
Peter.
Peter.
You there, Peter?
I think he's still joining.
Should we wait and let him do questions, or?
Yeah, it looks like it's having trouble coming in and out.
Okay.
Okay, Peter's now in the channel. I'm making him co-host again.
Sorry, guys, my laptop just froze up completely. I had to reboot.
That's a fast reboot.
Okay, well, now that you're back,
I'm back.
This was in the middle of your wrap-up slide, but
Yeah.
I think that we should all thank Peter for the talk. And now, since you're back before the time is over, I think we can field any questions. So Eric has a question. Eric, please go ahead.
Yes, thanks, Peter. That was a nice update, and I haven't seen you in quite a few years, so I was
It's
very
been a
happy
while,
to
yeah.
see that. No, so I had a question. I guess it was probably discussed last year, but so what came to my mind when you mentioned the troubles with A dot and A double dot is that you were generating runaway solutions, and of course that gives you an unstable evolution. So are you order reducing when you're evaluating A dot and A double dot?
I tried a lot of different things. So of course you have to do it using the data you have for A in the past, and so you have to store A at certain time levels. And of course you can store more than a single time level and try to take smooth derivatives to make things smoother. But I didn't find anything that actually worked. No matter how smooth I try to make the derivatives, and of course, if you make them smoother and smoother, then you also make them less accurate. I just didn't find anything that allowed me to do the full stable evolutions.
Okay, interesting. Thanks.
Okay, any other questions for Peter? So Peter, do you have any guesses at what's causing the convergence to be degraded to only first order?
I am not sure right now. I mean, I'm doing everything the same way as I do for what I would do at the boundaries of the world tube. And as far as I can see, it should still be, I should still get exponential convergence with the order. So I'm still a little bit puzzled, but I must be something really stupid, and I hope.
Or very subtle and deep.
Or it could be that it's very subtle and deep, but I mean, we have seen people do this before. So Scott Field and Hesthaven and Steve Lau did have a code where they used dispersal sources for DG scheme, and they didn't report any of this. So my plan is to go back and actually try to do some of the analytic, some of the examples they had in that code, and make sure I can reproduce that in my code. I'm sure it should be workable.
All right, next year.
Next year, yes.
Okay. All right, so let's thank Peter again, and now it's time for Samuel. So continuing with LSU. So Samuel, please take it away.
All right, thank you. So I am going to be talking about the gravitational self-force, doing, again, self-consistent evolution. Thankfully, Peter has given me a great introduction for that. Okay. So the basic goals of what I'm working on is to develop a time domain evolution code for the gravitational self-course using the effective source, or potentially, where we're shrinking it down to more like the delta function, like he's saying. All of that is likely to be applicable to the same thing. It's built in the same evolution code that Peter Diener has in the toolkits. This work is in the Lorenz-gauge, and so I'm also using 3 domains around it. I'm using around the source, I'm using tortoise coordinates. And then in the inner region, to the horizon, and from the outer region out to scribe plus, I'm using hyperbolical coordinates. So, of course, to derive the evolution equation, we all have already seen this several times. The first order perturbation equations for the trace reverse metric look like this. And we can decompose this into multipole harmonics like so. And these equations are basically just, oh, there's 2 pi's in that equation. That shouldn't be right, but that's fine. These are basically straight from Lousto. And so I do use this same sort of formulation. And then also, as previously mentioned, we can use constraint damping from like Goodluck et al., where you introduce this damping term in the evolution equations. And so kappa is just some constant, t is some time-like vector field, and z is the Lorenz-gauge condition. So in Brock and Lousto, they actually replace z with the z tilde that they define. I'm not doing that. I'm just using z as it is. However, the damping turns out requires some careful handling at the horizon. So I will revisit the struggles of the constraint damping a little later. So as I mentioned, I have these hyperbolical layers. So out to scribe plus, I'm doing it the same way as in Bernoulli et al. So there's 3 main things we want. We want the killing vector fields to be invariant across the interface. So when we transition from the t coordinate to the tau coordinate, we want those derivatives to be the same, which gives us a constraint on how our coordinates can vary. We want the outgoing null rays to be invariant across this interface. And then also, we're using compactifying coordinates to bring scribe plus into a finite coordinate radius. And then omega is defined to make all of that work. So that's just straight from Bernoulli et al. And then on the outer layer, I'm doing very similar construction. The main thing is instead of outgoing rays, I am preserving the ingoing null rays. So this just changes a sign in that initial definition. And yeah, and omega is defined. So again, slightly differently to make all of that work. So for the tensor spherical harmonic decomposition, I initially used the tensor spherical harmonics from Barak and Sago, which is just a minor change on what's in Barak and Lousto. It adds an f to the I equals 3. However, whenever I tried to use this basis, I ran into a lot of stability issues and some other problems. Thanks to some helpful advice from Barry, Niels, and Adam, I tried a different basis that instead of having, taking these linear combinations of the Barak-Sago variables, and this I have found a way to make these stable, although it's still a little problematic. So for both of these, though, the coupling matrix in the inner hyperbolical layer has singular elements at the horizon. And so these can be canceled by adding constraints to the evolution equations. However, in the case of the Barak-Sago variables, what this amounts to is actually changing the sign of the constraint damping. So it becomes constraint amplifying in the Barak-Sago variables, which is why they're unstable in that case. But that doesn't happen in this other basis. So yeah, as I mentioned, evolution using the Barak-Sago variables are unstable, even with constraint damping. And so initially, when I just used what I had from Barak-Sago into the new basis, it was still unstable. So I had to introduce this additional damping term in the inner region, which once I did that, I can now have stable evolution. I should mention this is just evolution of initial data on with the evolution equations. I have not coupled this to an effective source. There's not a source right now. This is just fields evolving. But yeah, so here's just a little thing of what the various regions have for their constraint damping for the equations. So it only appears in the equations for 1, 3, 4, and 8. The equation 3 has an F in it because it needs that to be finite at the horizon. And similarly, these 1 plus h's and 1 minus h's are to ensure that things are finite everywhere. Now, this additional C term that I've introduced in I equals 3 and I equals 4 and 8, this is that additional thing that it turns out when I added it, the evolution became stable. I'm not entirely sure what the exact requirements on this term are. I set it to C equals 100, and it's worked for all the simulations I've had. So I don't have a rigorous knowledge of what is required. I had it at C equals 50, but it turns out that whenever I increased the resolution of the run, that it was no longer stable. So there is something going on there that I don't fully understand what is required for it to be stable. But yeah, and the reason that it's where I have C times H is so that whenever it goes to the interface with the tortoise coordinates, that term goes to 0 because H is 0 at the interface. So here I just have some quick plots of what it looks like for L equals 2. And I have zoomed in plots, but we see that it has its, it's got the damped sinusoid general look and then just stays at effectively 0 after that. And this is for the reconstructed metric perturbations. So I just have all of them here. And so if we zoom in on the closer, just the first little bit, we see that after, the initial, it propagates out, that it, for the 0, 0 all the way down to like 1, 2, it more or less looks like just a damped sinusoid, but a lot of the angular ones have some sort of weirdness going on that I don't know what it's coming from. So they aren't just damped sinusoid, like a single damped sinusoid, especially 3, 4 and 3, 3 look particularly irregular, and I'm not sure what is causing that in my simulations. So this is all great, right? I now have it where I can actually simulate and run the evolution equations, and it's stable. However, when I look at the Q and M frequencies, I've got here. I've just cut it in further. I've got in the blue is the simulation, and in orange is what the theoretical Q and M is, which I generated using Leo Stein's code in the black hole perturbation toolkit. And we see that these clearly do not match. So for some reason, while the evolution is now stable and can run and just sit, once everything propagates out, it'll just sit at 0 for as long as I'll let it run. But something is still wrong with the Q and M modes, and I don't know what is causing that. So here I just have a quick plot. Or a table of data. So they're clearly wrong. So I didn't put a lot of work into getting really good numbers for the numerical, but I just estimated what the numerical frequencies were by plotting a damped sinusoid over the data and adjusting the frequencies so that it roughly matched, just overlapped with the data. And so with that rough measurement of the numerical frequencies, we can see here that they're clearly not the same. And so I have 2 L modes. I've run more L modes, but I've not actually, once I realized that they were clearly not right, I didn't continue comparing the numerical and analytic. But I could if there was some reason to do so. But yeah, so that's basically where I'm at. So right now, what I need to do is I need to determine what's causing these incorrect Q and M frequencies. And also at some point, restore the OpenMP parallelism that the scalar evolution code has. I took it out just to make sure everything was working fine. But obviously that needs to be put back in. And I don't know if I'll necessarily be doing this, but eventually there's, all of the existing hooks are already in there to bring in the effective source code, but it would need to be adapted a little bit to make it interface correctly. And then possibly I would need to refine the choice of damping once the effective source is in, because as I said, I'm not entirely sure on what is causing it to be unstable. So while I can currently make the evolution stable, that probably needs to be investigated a little more thoroughly, especially once the effective source is in, to determine what exactly that C coefficient should be. So yeah, and there's the references I have. All right.
Thank you, Samuel.
Mm-hmm.
Okay, questions for Samuel? Was that a question? Or is that a...
That was just a clap.
Oh,
nice talk.
Oh, Jonathan put a question in the text. Jonathan says, how did you determine the initial data?
Oh, right. Sorry. So I did 2 things. The first thing I did was it's just put a Gaussian in the time derivative of all of the 10 fields, which of course is not going to be constraint satisfying. And if I do that, and I plot the constraints, I see that while of course there's initially constraint violations, that those constraint violations all propagate out of the domain into the horizon or to Scry plus, and everything settles down to 0. But I also I have in the Mathematica notebook where it will generate initial data that's constraint satisfying. And when I do that, it is, of course, constraint satisfying at the start and remains so for the entire simulation.
So Jonathan has a follow-up, if you
Sure.
if you can see it there. It says, do the constraint violations damp out faster than the evolution data decays?
It's been a while since I looked at those plots, so honestly, I don't remember exactly how fast the constraint violations go away if I'm not using constraint satisfying data. I feel like they went away fairly quickly, but I can't say exactly how fast it was off the top of my head.
Okay, any other questions? I'm wondering, do you have code for generating initial data, the constraint satisfying initial data that scatters an ingoing pulse?
So the way I set up my initial data thing is I just set most of the h's to be 0 and then have time derivatives of a Gaussian and then left off just enough to basically be able to use constraints and time derivatives of the constraints to set the remaining fields and derivatives of the fields. So I don't know if that answered your question necessarily. I mean, I could use a different initial data if that would be useful.
Oh, I was just asking about the
Oh,
scattering data, just because it should, you know, ring up the quasi-normal modes. Well, you know, depending on the frequency content of the ingoing wave. So, you know, it's possible that the real quasi-normal modes are there, but just not being sourced sufficiently loudly. So there's some other strange oscillation, which I don't understand.
Yeah, I'm not really sure either.
I'm sure it can be done. We just haven't done it yet.
Jonathan is suggesting more initial data ideas in the text. A Tucholsky wave.
Okay. Yeah, I guess I could write that down. Yeah, but I can always try other initial data and see what I get or if that helps with anything. But right now it's just I set the fields to something and their derivatives, and then use the constraints and derivatives of the constraints to set the remaining fields and field derivatives. And that's just what I'm doing. So I don't know that it's necessarily a physically interesting anything going on. So there might be better initial data to get something that's more physically reasonable.
Okay, any other questions for Samuel? If not, then let's thank Samuel again. And is Carlos connected? I see Carlos here. Carlos, can you start sharing your screen? Okay. So I think we should take advantage of the fact that we're 2 minutes ahead of time. So you can unmute yourself and start whenever you're ready.
Thank you, Leo. So good morning to everybody. I hope you can see the picture of our center. I will use it to introduce a change of gears in the techniques that led to the results I'm going to present next. On the left side, you see the computers that are part of our lab for evaluating solutions of Einstein equations representing orbiting binary black holes. On the extreme right, there is one LIGO first generation folding mirror for the detection. And on the top, you see there is this talk will test your good sight. So the first test is to see a waveform on top, and this waveform for illustration on the long window has not been hand drawn, but have been computed by these supercomputers, and starting from 25 m of separation down to merger, these binary black holes perform nearly 100 cycles before merging together. So we are going to use full numerical techniques to evolve binary black holes. I presented, now I realize in Capra 14, 9 years ago, the first simulation of 100-to-1 mass ratio. That was a test case that allow us to evolve for 2 orbits before merger. I remember at the time, I think the meeting was in Southampton, Leo Barak was asking me if this was the end of the self-force technique, half joking, half serious. reassured him then that we were nowhere close to leaving you without a job. So that's still true in 2020. And the new thing I want to present is based on a study we did a couple of years ago for actually processing binaries. We wanted to see a system that would perform a complete flip of the orbital angular momentum, L, during merger, and if we could track this with full numerics. In doing so, you see here the plots of the orbits. That's again not my drawing. I couldn't draw such a beautiful flower by hand. This is actually how the orbit evolves and flips completely L. And in doing so, we had to come up with a very good set of grid structure to track this system. And we kind of hit a sweet spot. We compared with full numerics with PN, full numerics with PN, and everything works very nicely. So we kept this grid structure to scale to other even smaller mass ratios. In the meantime, in Capra 20 in Chapel Hill, I also presented a sequence of binary black holes, spinless black holes, in a small mass ratio from 1:1 to 1:10. And we could do fittings and extrapolations. So now we will use the new grid structures, techniques, and gauge choices to go from 115 to 132, 164, and 128 mass ratios. The result of the waveforms are summarized here. This is, well, an observer far away from the system, sees the waveform of the 15:1. That we started from a separation of about 12 m in proper distance. We did 32:1, I think 9.5 separation, 64:1, and 128:1 from, I think it was 8 m of separation. We'll see the table next. This is the second test for your site. If you can see the small black hole orbiting around the large black hole, you don't need glasses. Anybody can see?
Yep.
Again, this is an actual computation of the 128:1 to give you an idea of what these 13 orbits look like. I ask you to be patient for less than a minute to merge the curvature of the black hole. Horizon is depicted here in colors. This simulation took about 6-7 months on 8 nodes in Frontera. Again, what we did was study this 15:1 mass ratio in detail with 3 resolutions to check conversions of our algorithm. And we had computed, well, the remnant masses. We'll see what we can do with those. Spins in recoil velocity of the final black hole after merger. And for the waveforms, we compute the peak luminosity the peak, the frequency at the peak amplitude of the waveform. Essentially, we took the same grid, then 15 to 1, this proved to be convergence, very nicely behaved. So what we did is that the small black hole would reduce the mass to 1/2, but at the same time added a refinement level of half the size to take care of this reduced mass. And in this way, we evolved the case of 32 to 1. And then did the same, half the mass of the previous, add one more level of refinement, and then half the mass and one more level of refinement up to the 128 to 1 mass ratio, and compute the same quantities as above. These are the proper distance separation, how many orbits, between 10 and 13 orbits, roughly. And one interesting feature is that in doing so with the grid structure, the speed with the same, exactly the same research, computational resources, the speed only goes 1/2, essentially with 1/q, which compared to the 1/q to the 4th, if you would do a global refinement of the resolution. So it's much cheaper, it's feasible. In fact, we proved that you can do it. And I will try to convince you that it's accurate. So if we align all the cases to a common frequency, before I have shown you that you start at very different points. If you align all the initial frequencies and let them merge, this is how 15 to 1, of course, is more massive, emits more gravitational radiation, it merges faster. So from this frequency on, it takes 4 orbits for 15 to 1, 6 orbits for 32 to 1, 9 orbits for 64 to 1, and the 13 orbits that we have seen on the movie for 128 to 1. If you do a fit of this behavior, it goes like eta. Eta is the symmetric mass ratio as 0.5, which is a combination of the eta to -1 of the inspiral and the eta to the 0, independent of the mass of the plunge and merger. This is a detail of the merger. This is again the curvature of the trace of the extrinsic curvature of the spacetime at the horizon, and how the small black hole, rescaled here for visibility purposes, changes the curvature on the horizon. For the analysis, what we did was these formulas that fit what is the final mass, spin, and recoil velocity of the random black hole versus the initial mass ratio of the binary, and the same for the peak amplitude, luminosity, and frequency. The way you do this is, well, you look at the peak amplitude, what was the time of the evolution for this peak amplitude, pick up the phase of the same waveform at that time, and well, compute the derivative and gives you the frequency, and do this for each of the cases we study. You can do this for many simulations and different mass ratios and determine all these 3 coefficients in each of the quantities, the 6 quantities we want to study. So what I will show you here, another test of your good eyes, is that we did 2 things. I mentioned this work that I presented in Capra 20 in Chapel Hill, where we went from mass ratios 1:1 to nearly 10:1. And we did fit, and then you can extrapolate from this up to 10:1 to the 4 cases, 15:1, 32:1, 64:1, and 128:1. Again, I'm not fitting anything for the new simulations. I'm comparing the extrapolation of the more comparable masses for these 6 quantities with respect to what we measure now. Right? Here, for instance, for the frequency, for the peak frequency, you see that our extrapolation does not lie exactly on the computed peak frequencies, but they are off about 2%. Okay, so we are very happy with this test of our simulations. And so, as I mentioned, that changed a bit from Capra 14 in the sense that we could do now more accurately and 13 orbits compared to 2 orbits. And we have a way of assessing errors, typical errors, error bars. We estimate around 2%. We dealt with the non-spinning case, but the spinning, large black hole spinning case can be dealt with in a very similar way with this nice grid structure we found. And we hope that further improvements, I know, Capra 30 or so, we can do a massive production of this kind of simulations, at least for 3rd generation gravitational wave detection. And Lisa, if some of us plan to survive to it. Thank you very much for your attention, and I'm happy to answer any of your questions now.
Thank you, Carlos. You already have a question in the text from Mario Gutierrez Abed. If you don't see the text, I'll just read it. There are 2 questions, actually.
Yes.
Oh, no, it's just 1 question. For the 128:1 mass ratio simulation, did you use a fisheye grid or some new AMR technique?
No, I haven't used fisheye. I have chosen strategically, let's say, how you where you place the refinement levels. We have used 15 refinement levels for the 1 to 128 mass ratio.
Okay, it looks like Harold has a question.
Hi, Carlos. Very impressive results. Well done. I have actually 2 questions. First, in your movies, the little black hole looks too big. Did you do something funny there? Or is it really that big?
No, it is very, very small. We have to multiply by a factor for visualization purposes, but the track and the horizon quantities are faithful to the results of the simulation with Jonathan Thornburg, Apparent Horizon Finder Direct.
And my second question is, do you have a sense of your phase error that these simulations occur?
Yeah, that's a good question in the sense of what we compared with. So in the Q equal 15, we have convergence in extrapolation to infinite resolution. So we have I think it was 0.4 radians of errors. Here in the other runs, we don't have 3 resolutions. what we are doing is trying to compare with models like EOB, for instance, and see if this can give us an idea of what the phase errors are. But yeah, so what we are working on at the same time is actually we're trying to we are refining our gauges, and we found also a gauge choices for the lapse and the shift that we believe is improved. So we are rerunning this with something that we believe for the same resolutions will be more accurate.
Harold, did that answer your question?
Yes, fully, thanks.
Okay. Other questions? Are you going to make these waveforms publicly available, or are you going to do some other analyses with them first?
Yes, so we have actually a catalog that of waveforms of binary black holes that we keep updating, and now it comes a third release that will include many waveforms around, well, exactly 777. So our policy is to make them publicly viable. So we want to do first some analysis on these ones. We are in fact doing some analysis. People interested, please contact us, and we can we can share on targeted studies. But eventually, yes, they will be available publicly in our site, RIT catalog.
Yeah, I think that these waveforms could probably be very useful for the post-adiabatic waveform modeling.
I think, yeah, so my advice on this side would be to take the 15-to-1, where we, as we were discussing, we have a good idea of where errors lie. So you can see when you compare to other approximations what you know what to expect regarding accuracy. The other cases, yeah, they are indicative. I mean, we know in numerics that a number doesn't mean match unless you can provide a plus minus after that. But yes, I mean, one can try and see how far one approximation versus the other is, or if you were thinking of matching, that's the one part that I would be very careful about.
It looks like Lior has his hand up. Let's let Lior get the last question.
Can you hear me?
Yes.
All right. Amazing results, Carlos. Is it not possible to do a convergence test for the 128 just by doing lower resolution runs?
Yes, that's what we are doing. But you need 3 of them. So lower is really low for us. That's what we are doing. The next one, but if this one took let's say 6 months running, a higher resolution one will take 1 year. So maybe for next Capra, I can together with Peter Diener's resolution of his A dot and A2.2 problems, we can have a fantastic Capra 24 with all these results.
Okay, I think it's time to move on. So let's thank Carlos again. And
thank
Carlos,
you,
could you please stop sharing your screen so that Marcelo can share his?
Also, I'm going to pause the live stream for this talk just so it doesn't get recorded for those